good morning all. So today we have Dr. Tricia alias Princy Paulos ma'am with us. So she will be dealing with the topic analysis of drugs and pharmaceuticals part 2. We all are familiar with her. She has also taken the first session also. Before starting session, let me have a brief intro about her. So she is presently working as assistant professor, Department of Chemistry, Bishop Moore College, Mavelikara. She did her post-graduation in applied chemistry from 𝐶USAT and PhD from University of Saskatchewan, Canada. She did her postdoctoral research from University of New Brunswick, Canada. She worked as a research associate in University of Kuwait. And so far, she also she got 8 research papers published so far from there. So good morning, good afternoon, ma'am. Welcome to the session, ma'am. And to all the attendees who are attending the session, I have a small request. So we will have a 1-hour session with us. So we will have 2 breaks. First break will be after 20 minutes. If more questions have been raised by the students, we will have a break. And if there's no questions raised by students, we will continue with the session. And before winding up the session, before 10 minutes before the session, we will have another Q&A session. We will have a question answer session. So attendees, please be calm and raise your doubt to ma'am. So ma'am, I'm handing over to you. You can just start the session.
Thank you, Balu. Welcome everyone to my talk today. My talk today is on the analysis of drugs and pharmaceuticals. This talk is primarily designed for the S4 MSc Analytical Chemistry students of University of Kerala. And I've already taken 2 talks earlier, which dealt with the 3 parts of this module. There are 4 parts to this module, and I've already dealt with the first 3 parts. So today is the final part of this module, which is analysis of drugs and pharmaceuticals. So let us go straight into this. So before I go into drugs and pharmaceuticals, I think quality control, we have to discuss about quality control a bit. Quality control is a very important aspect of all industries, especially pharmaceutical industry. So quality control, what do you mean by quality control? So all the processes, all the measures, all the procedures that are undertaken to ensure the quality of a drug, so that the quality coming out of a company, of a production unit is of good quality, those are called quality control. That is called quality control. So these are the measures to ensure that the drug is of good quality, or the pharmaceutical is a good quality drug. So it is a very important part of a pharmaceutical industry because it ensures the marketing of safe and effective drugs that meets all the regulatory criteria of the country or of which is needed. And also it establishes good standards, good quality standards for production of good quality drugs in an economic fashion. Also, quality control checks the quality of every batch which comes out of the production unit. So to make sure that every batch reaches the quality standards of which is needed. And so every batch has to be analyzed. Also, when you have a good quality control, it accelerates the sales of that product, because good quality products are always in high demand. So a good quality control will help you to accelerate the sale of that product. Also, quality control helps, or it boosts the development of very high-end sophisticated techniques and methods for evaluation of the drugs. It also helps in the production of better and novel medicinal drugs. Also, the quality control department has to work hand in hand with the quality assurance and the research and development departments. And there are 4 main responsibilities of the quality control department: is to ensure efficacy, safety, quality, and compliance, so that the drugs coming out meets the regulatory requirements of the company and of the country. So, what are some of the roles and responsibilities of What are some of the roles and responsibilities of quality control? So first of all, the quality control the department has to, or the laboratory has to test and verify the quality of all the products, of all the starting materials, raw materials, against predefined standards. So they have to test in-process products also, the final pharmaceutical FPP, final pharmaceutical product also, the raw materials, the packaging materials that have been used. They also have to test for the shelf life of the drug, the stability of the drug. We also have to test the standards that are employed in the drug, the working standards and the reference standards. They have to test for heavy metals. They have to test for sterility. Sterility testing has to be done. Bacterial testing has to be done. There is microbial limit testing, bioburden testing. So all kinds of testing has to be performed before a drug enters the market. So the techniques they can be used that are there are chemical techniques, physical techniques, there are microbiological tests, and various other techniques are used. Several techniques are used in the quality control laboratory. Also, the quality control laboratory has to analyze and study any deviation in the quality of the products. If maybe in any batch there is a deviation in any of the quality, or they have to study that. They have to study the extent of deviation, and also they have to come up with corrective measures to correct those faults or those deviations or those issues with the quality of the drug. So they have to come up with corrective measures also. And also they have to deal with the complaints, the product recall. Sometimes the product enters the market, but before it is distributed, the company realizes some problem with the product, and then they recall it back from the market. So that's called product recalls. Also, sometimes products are delivered to the consumers, and then they have to call it back. That's the returned product. So all these products they have to test, analyze, they have to check where they go, where they went wrong, what was wrong with their product, what was wrong with the quality of their product, and they have to ensure that such things don't happen, and the quality should not be compromised at any stage. That's why quality control is of utmost importance, especially in a pharmaceutical company. So, what are the different types of methods that is used for ensuring quality of a drug? There are different analytical methods and analytical processes that are used in laboratories for pharmaceutical testing. There are the standard methods that are used, and by standard methods, those methods which are accepted by the national board or by international guidelines such as ASTM, American Society for Testing and Materials. Then there is the International Organization of Standards, the ISO. There is IUPAC, the International Union of Pure and Applied Chemistry. So all these international and standard guidelines have to be used in standard methods. So these are the standard methods which have been accepted worldwide. And it is described by the legal regulations. So these are legal methods or official methods, you can say. Then there are the laboratory procedures, common or comparable laboratory procedures. These are not the official methods or the standard methods, but they are accepted because they have been verified and they have been considered to be equivalent to standard methods. Then there are the other analytical methods. These might not be, again, the official methods or the methods accepted by laboratories in government regulated areas. These might be the latest analytical procedures which have not yet been established. So those are other methods. And then, of course, there are field methods. Field methods are for performing tests outside the laboratories in the fields or in mass amount. So outside the laboratories, the tests that are conducted are called field methods, and these need not be quantitative. They can be semi-quantitative. They can give semi-quantitative results as well. Okay, so these are the different methods. So now let's look at some of the official methods. Now, what do you mean by official methods? Okay, before coming to the official methods, let's look at the official methods first. So when we talk about official methods, the word pharmacopoeia comes up. I don't know how many of you are familiar with the word pharmacopoeia, but it's a very important word in the drug industry. A pharmacopoeia is nothing but it's a document. It's basically a book. It's a document. It's a legally binding collection of standards that are used, standard testing procedures, standard methods that are used in laboratories, so that a drug becomes legally acceptable for marketing the drugs in the marketing the drugs. So ഒരു ഡ്രഗ് മാർക്കറ്റ് ചെയ്യണമെങ്കിൽ ആ ഡ്രഗ് അതാത് രാജ്യത്തിന്റെ ലീഗൽ റെഗുലേഷൻസ് അക്സെപ്റ്റ് ചെയ്തിട്ടുള്ള അല്ലെങ്കിൽ അതാത് രാജ്യത്തിന്റെ ഫാർമക്കോപ്പിയ അക്സെപ്റ്റഡ് പ്രൊസീജിയേഴ്സ് വഴി വേണം ടെസ്റ്റിംഗ് ഒക്കെ നടത്താൻ. സോ every country, maybe every country has India has its own pharmacopoeia, the Indian pharmacopoeia. So a pharmacopoeia, as I said earlier, is nothing but it's just a book. It's a book of all official methods of testing and procedures. The quality specification to confirm the identity and the purity of the product, the strength of the API. API is the active pharmaceutical ingredient. To test the starting materials, to test the intermediates, to test the final pharmaceutical product, test the excipients. I don't know if you're familiar with the word excipient, but excipients are, so excipients, what are excipients? Excipients are added with the drug, with the active pharmaceutical ingredients. If you take a tablet, the tablet contains the active pharmaceutical ingredients, but other than that, there are also several other things which are incorporated in the tablet. Those are called excipients. For example, there might be a component for bulking up the pharmaceutical. Maybe the concentration, the amount of API needed is very small. So for making it easy to handle or to bulking up the drug, we add a bulking agent, or which is called fillers. You can add flavoring agents. You can add stabilizers, which stabilize for long-term storage. Stabilizing agents are added. You can have coloring agents. You can have coating agents on a tablet to have a smooth surface or a protective layer, so that that there is no it doesn't interact with moisture or air, and the tablet is safe. So these are all different types of excipients that can be used in a tablet or in a drug. So the pharmacopoeia, all these things, the different types of tests that has to be carried on for the quality testing of the drugs. Not just the drugs, but also the excipients, the added ingredients which comes together with the drugs, the active pharmaceutical ingredient. So that book is called the pharmacopoeia, book of all standard procedures. The book also consists of monographs. The book contains, like, for every pharmaceutical drug specification, the reference for every pharmaceutical drug specification, that's called monographs. So it is made up of monographs. So pharmacopoeia, as I said earlier, can be national, it can be regional. National pharmacopoeias are, there is the British pharmacopoeia, there is the Japanese pharmacopoeia, there is the Chinese, we also have the Indian pharmacopoeia, or it can be regional also, like the European pharmacopoeia. We also have the international pharmacopoeia by the World Health Organization. So there are different kinds. Then the American, which is called the USPNF, which is United States Pharmacopoeia National Formulary. The American Pharmacopoeia comes in two parts. The first part, or two official books, or two official documents, or two official compendia, as they say. First is the USP. USP is the United States Pharmacopoeia, which consists of monographs for drugs and for the medicinal products, and the National Formulary, which is the second document, which is for the excipient monograph. So that is the additives together with the APIs. The Indian Pharmacopoeia, which was established in 1956, it is derived from the British Pharmacopoeia, and it sets the standards of all drugs that are manufactured, sold, and consumed in India. And there are several techniques. So all the analytical techniques that you see, the modern analytical techniques that you see have been incorporated in the Indian pharmacopoeia. There's the infrared, there's fluorimetry, there's UV-vis, NMR, conductivity, and so on, all the modern techniques. So if a drug is sold out without meeting the regulation of the national regulation of the national pharmacopoeia, then it is considered a criminal offense. So it's a very serious issue. So if you take any drug or any syrup or any tablet, if you have lying down at home, you check it out. The ingredients in the drug is labeled. When it's labeled, at the end they have the acronym IP. IP stands for International Pharmacopoeia. So that's how the drugs have to be labeled, whether to make sure that the consumer is also feels safe, that they are having consuming a safe drug, to make sure that that drug is produced meeting all the regulations of that country. So this pharmacopoeia is a very important document in the pharmaceutical industry. Which contains all the official methods. Now let's look at some of the first methods which were there for the analysis of drugs. They are called the classical methods. And they are also some of the earliest methods, and they are wet chemical methods. And by wet chemical methods, because they use mostly the chemical property, substance and the chemical property വെച്ചിട്ടാണ് അതിന്റെ അനാലിസിസ് ചെയ്തുകൊണ്ടിരുന്നത്. അപ്പൊ അങ്ങനത്തെ ഡ്രഗ് അനാലിസിസിൽ നമുക്ക് ആദ്യം നോക്കാം എന്തൊക്കെയായിരുന്നു സെപ്പറേഷൻ ടെക്നിക്സ് പണ്ട് ഉപയോഗിച്ചിരുന്ന സെപ്പറേഷൻ ടെക്നിക്സ് എന്തൊക്കെയാണ്. ഇപ്പൊ പ്രസിപ്പിറ്റേഷൻ അല്ലെങ്കിൽ എക്സ്ട്രാക്ഷൻ അല്ലെങ്കിൽ ഡിസ്റ്റിലേഷൻ പോലത്തെയുള്ള ടെക്നിക്സ് ആണ് പണ്ട് സെപ്പറേഷന് വേണ്ടിയിട്ട് ഉപയോഗിച്ചുകൊണ്ടിരുന്നത്. ക്വാളിറ്റേറ്റീവ് ടെക്നിക്സ് എന്ന് പറഞ്ഞാൽ അതിന്റെ കളർ, ഒരു കമ്പോണന്റിന്റെ കളർ വെച്ചിട്ടോ അല്ലെങ്കിൽ ഓർഡർ വെച്ചിട്ടോ അല്ലെങ്കിൽ എന്റെ മെൽറ്റിംഗ് പോയിന്റ് വെച്ചിട്ടാണ് എന്നെ ക്വാളിറ്റേറ്റീവ്ലി ഐഡന്റിഫൈ ചെയ്തിരുന്നത്. അതുപോലെ ക്വാണ്ടിറ്റേറ്റീവ് അനാലിസിസിൽ two common methods of analysis was gravimetry and volumetry. അപ്പൊ ഇത് രണ്ടും നമ്മുടെ ലബോറട്ടറീസിൽ സ്റ്റുഡൻസ് ഒക്കെ ഇഷ്ടം പോലെ ധാരാളം ചെയ്തു വരുന്ന ടെക്നിക്സ് ആണ് gravimetry, volumetric techniques. So those are some of the qualitative, those are some of the classical methods that were used in earlier days of drug chemistry. The modern techniques, such as has evolved from these old classical methods. For example, the volumetric methods. Volumetric methods have evolved drastically. So, for example, the non-aqueous titration of weak acids and weak bases, which is not possible in the aqueous counterpart, in the aqueous volumetric titration. It's not possible to do weak acid, weak base titration. But in non-aqueous titration, it was possible to do weak acid, weak base titration. Also, the potentiometric titration. All these modern, these are all, it has all evolved from the classical methods of classical volumetric technique, and they are very precise, sharp endpoints, and so on. And also, volumetric techniques has evolved into, it has found its way into kinetic analysis. Kinetic analysis ചെയ്യാനും functional groupനെ കണ്ടുപിടിക്കുന്ന കുറെ ടെസ്റ്റുകളുണ്ട്. ആ ടെസ്റ്റുകൾ ഉപയോഗിച്ചിട്ട് we can also do kinetic measurements using volumetric titration. So what are the advantages of these techniques? Advantages എന്ന് പറഞ്ഞാൽ ഒന്നാമത് സമയം ലാഭിക്കാം, save time, it is cheap, it is also efficient, it's also saves labor. Very high precision, there's no need for reference standards and so on. So some of the examples of titrations that have been used in the drug industry is the titrametric methods, which is used for lisinopril. Lisinopril is a drug which is used for BP, blood pressure. Albendazole, which is for treating worms. Then there is gabapentin, which is used, I believe, for seizure treatment, and so on. There are many such sparfloxacin, which is also being analyzed using non-aqueous titrations. Titrametry can also estimate the degradation products of this drug. So basically, you can say that gravimetry and volumetry were the backbone of the classical methods of analyzing drugs. So what are the modern methods? Let's look at some of the modern methods that we use. these days. Modern methods are mostly instrumental methods, and they use physical properties of the analyte. The chemical methods, they use the chemical properties, whereas the modern methods use the physical property of the analyte. Physical properties such as the absorbance, light absorbance, or the fluorescence, or the chemiluminescence, conductivity, and so on. There's all sorts of physical properties which have been used for modern analytical techniques. In the modern techniques, the separation is being done mostly by chromatography. Chromatography is I would say, the major way in which separation of components of a mixture is carried out. Then there is also electrophoretic technique. Then for quantitative analysis, we still use titometric, different types of titometric analysis, potentiometry methods, and so on. Then there is chromatographic techniques. Chromatographic techniques, we use TLC, HPLC, paper chromatography. There is column chromatography. There is gas chromatography. There is liquid chromatography. There is the HPLC, higher-end HPLC, high performance liquid chromatography, and so on. So many modern techniques are there right today. Modern chromatographic techniques are in use. Then looking at the spectroscopic techniques. Spectroscopic techniques, there is colorimetry, where you measure the absorbance of the compound at a particular wavelength. That's colorimetry. There is UV visible spectrophotometry, where you measure the absorbance in the UV visible region. There is fluorimetry, where you measure the fluorescence of the compound, and so on. There's electrophoretic methods are also there, such as capillary zone electrophoresis. There's kinetic methods of analysis. The stopped flow systems are there. These systems are used for analyzing or studying very fast reactions. So you just mix the two reactions and you immediately test it. You have the detector right there in the cell where you mix the two reactants, and you immediately test. As soon as the cell is full of the sample of the mixture, you measure it detects it automatically. The detector automatically senses it and reads the concentration or measures the concentration of the analyte. There's the flow injection analysis and also several hyphenated techniques, where you have a separation technique clubbed with the detector. So separation techniques such as HPLC, the chromatographic technique, electrophoretic techniques like the capillary electrophoresis, they are linked to a detector such as an IRs or a UV vis spectrophotometer or a fluorescence emission NMR spectrometers, and so on. So some of the hyphenated techniques which are used in modern analytical laboratories are LCMS. So liquid chromatography hyphenated with a mass spectrometer detector, or a GC hyphenated with a mass spec detector. Then you have the LC, which is hyphenated or which uses the NMR as a detector. And you have the ICP, inductively coupled plasma, where you have mass spectrometer again as a detector. So there are several such hyphenated techniques. So these are just a few. There are several more that you might have studied or you might have not studied. So these are the modern methods of analyzing drugs in the body. They are mostly, as I said, instrumental techniques rather than wet chemical methods. Moving on. Now let's look at some of the common drugs that we use, and let's see what are the analytical methods or analytical techniques which are used for these drugs. So the most common drugs that we use are analgesics or antipyretics. What are they? Analgesics are used to reduce pain. It's used to relieve or reduce pain, such as paracetamol and aspirin, ibuprofen, brufen or ibuprofen. So these are some of the analgesics. Their main function is to reduce pain or to relieve pain, alleviate pain. And antipyretics, their main function is to reduce the body temperature, to reduce fever. Some of the examples are aspirin, ibuprofen, acetaminophen. So most of the analgesics, they are also used as antipyretics. And some of the common analytical techniques that you use for their analysis is titrometry, volumetric titrations, chromatography, TLC, column chromatography. You can also use UV-vis spectrophotometry. There is also potentiometry. Now let's look at some common analgesics and antipyretics. For example, let's look at aspirin. Let's look at aspirin. Aspirin is acetyl salicylic acid. So qualitatively, if you just want to identify the presence of this drug, of aspirin, this particular drug, you can do that by the ferric chloride test. So ferric chloride is first hydrolyzed with salicylic acid, and then using neutral ferric chloride test, you can identify this particular compound because it gives a violet coloration with neutral ferric chloride. It is the formation of the complex with ferric ions. Then we have the volumetric test, in which you take your drug and then you add a known amount of sodium hydroxide whose concentration is known. So a known excess of sodium hydroxide is added to the drug, and the excess, so the sodium hydroxide neutralizes the carboxylic group of the paracetamol, of the aspirin, and the excess sodium hydroxide is used to sorry, my phone is ringing. Okay, the excess sodium hydroxide is titrated with standard hydrochloric acid using phenol red indicator. So the instrumental methods that we can use is, of course, HPLC can be used, high performance liquid chromatography, using acetonitrile water as the mobile phase, and UV-vis detector or a PDA detector. PDA detector is similar to a UV-vis detector, but the main difference between a PDA detector is that the detector can scan the entire range of UV-vis spectrum. Whereas in the case, if you're using a UV detector or UV visible detector, you have to select a certain wavelength of which the absorbance of which is measured. But for UV-vis, you don't have to select a particular wavelength. It scans the entire spectrum of UV-vis. So that's the PDA detector. So that's how you analyze for aspirin. For paracetamol, this is paracetamol. It's an amide. It has an amide group, CONH group. For qualitatively testing for paracetamol, you can test it using potassium dichromate, because it gives a violet color with acidified potassium dichromate, changes basically oxidation state of chromium. Colorimetrically also you can test for paracetamol. Paracetamol forms a yellow Schiff's base, an amine compound with 1% 2,4-dinitrobenzaldehyde, and that colored compound can be measured in the visible region at 435 nanometer. You can also use UV spectrophotometry using sodium hydroxide solution of paracetamol absorbed at 257. So those are some of the analytical methods for paracetamol. In the case of ibuprofen, this is the structure of ibuprofen. So for qualitatively testing for ibuprofen, you can use TLC. Via TLC, you can test the presence of ibuprofen using hexane, ethyl acetate, and glacial acetic acid as the mobile phase. And then you use, for developing the TLC phase, you can use 1% potassium permanganate solution in sulfuric acid, heat it to 180 degrees Celsius for 10 minutes, and then you can measure the absorbance at 365 nanometer in the UV region. Titrations, volumetric titration can also be done for the analysis of proofing. You first powder the tablets, you extract it with ether, you evaporate it, you dissolve it then in methanol, and then you titrate it against standard sodium hydroxide solution using phenol red as indicator. There are UV spectrophotometric methods also, because proofing absorbs at 264 nanometer in using chloroform as a solvent. So those are the methods that you can use for analyzing ibuprofen. So these are the three. So we looked at aspirin, we looked at paracetamol, how to test for paracetamol, we looked at how to test for brufen. So some of the common, so these are some of the common analgesics and antipyretics that are used. Now let's look at anti-malarial drugs. Anti-malarial drugs, when we talk about anti-malarial quinine comes up. So how do you test for anti-malarial drugs? So for anti-malarial drugs, mainly you use high performance, high pressure liquid chromatography is used, which is the instrumental method. So you powderize, you pulverize the tablets, you extract it in a suitable solvent and you sonicate it, centrifuge it, and the supernatant liquid is injected into the HPLC. So you can hyphenate the HPLC with a UV detector or a PDA detector, a photodiode array detector. And such techniques have been used in analyzing for chloroquine, quinine, amidoioxin, mefloquine. So these are some of the anti-malarial drugs which are available in the market. You can also use GC in case if you have a non-polar volatile derivative is possible. If you can make a volatile derivative of your drug, then you can also go for gas chromatography, because in gas chromatography, one important aspect necessity is that you have to volatilize your sample. So if it is possible to volatilize your sample, to convert it into a volatile derivative, you can also go for GC and you can club it with a mass spectrometer as a detector. An example of is mefloquine. Mefloquine is an anti-malarial drug which is analyzed using this particular GCMS technique. There's also fluorescence methods for anti-malarial drugs have been used. TLCs have been used, thin layer chromatography. I'm not describing each method because I think you are familiar with all these techniques. Thin layer chromatography, GC, HPLC. You have all studied these techniques. In the same paper, the first module is about chromatographic separation technique. So that's why I'm not elaborating on these techniques. So for antimalarials, you can use, these are the techniques that you can use: HPLC, GC, fluorescence methods, TLC. There are also analytical techniques. You can also do blood assays, not only for analyzing drugs, but if to measure the content of these drugs in your blood, you can do blood assays also using these same techniques. You can do them. Urine for also not only blood but also for analyzing the concentration of these drugs in urine also can be determined using these techniques. Urine, it is more semi-quantitative, but the rest of these techniques are highly quantitative, gives precise concentration of the drugs. Next, anti-malarial. So we looked at antipyretics, analgesics, anti-malarials. The next type of drugs that we are going to look at as anti-allergic drugs, which are also called antihistamines. So as the name suggests, anti-allergic drugs are drugs that treat allergy, any kind of allergy. Have a sneezing or a runny nose or nasal congestion, which is caused due to maybe animal allergy or dust allergy, or allergies due to certain pollen, of certain flowers, flower which starts blooming in certain seasons. So seasonal allergies are also there. So all those drugs that treat allergies are called antihistamines. These are very cheap drugs. And some of these drugs you can get also over-the-counter drugs. You don't need a prescription. This is a prescription band. Pharmacy in the drugs, antihistamines, anti-allergic drugs. Anti-allergic drugs, antihistamines. So what are histamines first? Histamines, it is a compound. It's an organic nitrogen-containing compound, histamine. Or imidazole ring und or amine group of end on that imidazole ring, a chain with an amine group at the end. So that is histamine. It's an organic compound. And what does this histamine do? It has mainly three functions. Histamines, the primary function, it induces or it starts local immune responses. Start ചെയ്യാനായിട്ടുള്ള ഒരു main compound ആണ് ഈ histamine. അതേപോലെ തന്നെ physiological function ഉണ്ട്. Gut regulates the physiological function of our gastrointestinal tract. And it also acts as a neurotransmitter to the brain and the spinal cord. So these are some of the main functions of histamines. Organic compound in the main function. Histamine receptors proteins. ആ പ്രോട്ടീൻസ് ഈ ഹിസ്റ്റമീൻസ് ഈ പ്രോട്ടീൻസിനെ ബൈൻഡ് ചെയ്യുമ്പോഴാണ് ബോഡിയിൽ ആ ഒരു ഇഫക്റ്റ് certain effects start taking place. So those are called the proteins which take up the histamine. So the histamines, they bind to certain types of protein, and these proteins are called histamine receptors. Now the main there are 4 types of histamine receptors. There is the H1, there is the H2 receptors, there is the H3 histamine receptors, and the H4 histamine receptors. ഇനി ആന്റിഹിസ്റ്റമീൻസ് എന്താ ചെയ്യുന്നത്? ആന്റിഹിസ്റ്റമീൻ ഈ റിസെപ്റ്ററിന്റെ ആക്ടിവിറ്റിനെ അങ്ങ് ബ്ലോക്ക് ചെയ്യും. It stops the function of the receptors. Histamine binding on a block here. That is what antihistamines do. It blocks the function of the histamine receptor. So, H1 antihistamines, H1 histamine receptors ne block here. H2 antihistamine, H2 histamine receptors ne block here, and so on. So there are primarily രണ്ട് തരത്തിലുള്ള antihistamines ഉണ്ട്. ഒന്ന് H1 antihistamine receptors, H2 antihistamine receptors. അങ്ങനെ രണ്ട് മെയിൻ ആയിട്ടുള്ള antihistamines ഉണ്ട്. അതിൽ H1 antihistamine receptors ആണ് വൈഡ് ആയിട്ട് യൂസ് ചെയ്തുകൊണ്ടിരിക്കുന്നത്. ഈ H1 antihistamine is also the second most widely used medicine, just second to antibiotics. So antibiotics are unfortunately is the most widely used medicine. And second to that is H1 antihistamine, which are the allergy drug. So I think you understood, kind of got an idea of what these antihistamines or anti-allergic drugs are. So now let's look at how do you analyze these drugs. So for that, first let's look at what are the types of antihistamines which are there. There are 3 types basically: the first generation, the second generation, and the third generation antihistamines. And the first generation, it's more sedating. It has a sedating effect, and these are not used much these days. The second generation and third generation are widely used. The second generation is relatively less sedating. There are more new drugs. For example, cetirizine over-the-counter antihistamine, cetirizine, Avastin. They are more of selective peripheral H1 antihistamine, H1 histamine receptors, blocking drugs. In the third generation is completely non-sedating drugs. This third generation kittunnathu ee second generation, old second generation drugs inde isomers ആയിരിക്കും third generation. അല്ലെങ്കിൽ പിന്നെ അതിന്റെ ഏതെങ്കിലും ഒരു മെറ്റബോളൈറ്റ്സ് നെയാണ് third generation antihistamine drugs ആയിട്ട് പറയും. It is derived basically from second generation antihistamine. ഇവിടെ രണ്ട് എക്സാമ്പിൾ ഞാൻ തന്നിട്ടുണ്ട്. സോ ഇത് സിട്രസിൻ ആണ്. This is the active pharmaceutical ingredient which is present in your cetirizine tablet. Cetirizine tablet present ആയിട്ടുള്ള ഒരു ഈ കോമ്പൗണ്ട് ആണ് ആന്റി അലർജിക് ഇഫക്ട്സ് തരുന്നത്. സിട്രസിൻ അലർജീസിന് നമ്മൾ സാധാരണ ഉപയോഗിക്കുന്ന ഒരു ഡ്രഗ് ആണ്. പിന്നെ ഉള്ളത് ലോറാറ്റജിൻ. Loratadine is also another antihistamine drug. It is commonly called as Claritin. Claritin എന്ന് പറഞ്ഞിട്ടാണ് മാർക്കറ്റിൽ ഇത് വിൽക്കുന്നത്. Loratadine ആണ് ഇതിലെ active pharmaceutical ingredient which causes the anti-allergic effect, brings about the anti-allergic. Okay. So let us see how to analyze these drugs. So for analysis, there are several methods for anti-allergic drugs. There are several methods that are used. So let's look at it one by one. So the first are the spectroscopic methods. So first, let's look at the spectroscopic method. Spectroscopic methods, there are several types. Again, there is the UV spectrophotometry, in which the compound absorbs, or the drug absorbs in the UV region, and from the absorbance you can relate that to the concentration of the drug, and you can find out the concentration. In UV spectrophotometry, there is actually 3 different kinds. There is direct UV spectrophotometry, there is derivative UV spectrophotometry, there is also chemometric. Direct methods are what we use normally. We measure the absorbance, we measure at a certain wavelength. So you scan the wavelength and you measure the absorbance. So it gives you a spectrum of absorbance versus wavelength. There is a derivative UV spectrophotometry. spectrophotometry, you get a derivative. It can be a first derivative or it can be a second derivative. So you basically have a graph with delta A, or the change in absorbance, versus delta lambda, the change in wavelength. You can also have a second derivative where you have the delta square A versus the delta square lambda. So second derivative. So those are called the derivative UV spectrophotometric methods. There's also chemometric methods where it's more of employing mathematical models and statistical models are applied. So those are the UV spectrophotometric methods. So I've given acronyms for this drug, and the full form I've given. There's somewhere in the slide. This stands for CTZ is for cetirizine, LOR for loratadine, EBS for Avastin, FXD is for fexofenadine, and so on. The next is visible spectrophotometry. Here, those drugs which absorb in the visible region. So, or sometimes the drug doesn't absorb in the visible region. So, what do? You either make a charge transfer complex with that drug, where the drug acts as the end donor with either pi acceptors or sigma acceptors, or you can also make it into an ion pair complex. The ion pair formation can be carried out, or you can also study some type of redox chemistry with that drug, and study that, and the output of which can be analyzed using visible spectrophotometry. So there are different ways in which, even if your drug doesn't absorb in the visible region, there are different ways in which you can analyze the drug in the visible region using visible spectrophotometry. There's also chemiluminescence. Fexofenadine has been analyzed using chemiluminescence spectroscopy, where the chemiluminescence, you may convert the drug into with a certain, you add it, react it with a certain component so that the product becomes chemiluminescent, and you measure the chemiluminescence of the drug. There's also atomic absorption spectrometry, where the drug is reacted with cobalt thiocyanate. It forms a ternary complex. Then you estimate the concentration of cobalt in that complex, and indirectly you can get the concentration of the drug. There's also flow injection analysis, where you have flow methods that you inject the sample into a flow of a reagent, at the end of which there is a detector placed. The detector could be chemiluminescence, could be UV-vis, could be fluorescence, and so on. So there are several methods in spectroscopic techniques alone for analyzing history. Other than spectroscopic methods, we also have chromatographic methods, of course. There's the thin layer chromatography. There's also the HPLC, high performance liquid chromatography, coupled with or hyphenated with a UV detector or fluorescence detector, or even a mass spec MS detection is also possible. There's also the GCMS. Ketotifen and loratadine has been analyzed using GCMS methods. Then again, we have capillary electrophoretic methods, where capillary zone electrophoresis is coupled with UV detection to analyze the concentration of the drug. There's electrochemical methods like voltammetry, cyclic voltammetry, differential pulse voltammetry. There's potentiometry, polarography, where you have the dropping mercury electrode is used. So several types of electrochemical methods are there, and I'm sure you have heard or you have studied some of these methods. For example, cyclic voltammetry, you basically change. There's a change in the potential of the working electrode, and you measure a certain component. You change the potential, the current. Differential pulse polarimetry, voltammetry is in which you change the change in current at a certain potential as is plotted. The change in current is plotted against the potential change over the potential. Then there is also titrometric methods, of course, the volumetric methods. There's coulometric methods, where you are measuring current, which is related to the concentration of the analyte. There's also the potentiometric methods, where you're measuring the potential, which is related to the concentration of the analyte, the potential difference, which is related to the concentration of the analyte. So several methods are employed, and all these, if you look at these, they're also, most of these methods are official methods. These modern and also the modern methods which are employed in drug analysis. Next, let's look at antibiotics. And this is the last section, antibiotics. Antibiotics are basically antibacterial. You can say they are antibacterial agents or antimicrobial agents that destroy or inhibit the growth of microorganisms and are used in the either the treatment or prevention of bacterial infections. So, adhaneyana antibiotics. So, antibiotics can be basically classified into three types. There are three different types of antibiotics. The first type is the biological or natural product antibiotics. These antibiotics are produced a fermentation process vary ഉണ്ടാക്കുന്ന antibiotics natural antibiotics, a fermentation process. So it's from natural products. It's obtained from natural products via fermentation, and therefore it is called biological or natural product antibiotics. The problem with these is they contain a lot of unpredictable impurities. You cannot have a good control on the production of these drugs. Variability, the products are variable, there's complex impurities. And some of the common examples of natural antibiotics are aminoglycosides, macrolides, tetracyclines, etc. The second type of antibiotics is synthetic antibiotics. These are drugs which are synthesized in the laboratory. For example, penicillin, the first antibiotic discovered, penicillin, by Alexander Fleming. That drug actually was later chemically synthesized. So what we use now are the chemically synthesized drugs. It has a lot of intermediate compounds which comes during, which is produced during the synthesis. A lot of intermediate compounds are there. So for some of the drugs which are synthesized in the laboratories of synthetic antibiotics are sulfonamides, quinolones, oxalidones, etc. Then there is a semi-synthetic antibiotic. It is partly synthesized in the laboratory and partly from natural products. So it's a mixture of both. So it contains actually both kinds of impurities. There are impurities which are produced, which we get from the natural products also, and impurities which are formed during the synthesis part also as intermediates. So they have both types of impurities present in them. Some of the examples are beta-lactam. Penicillin is also produced in a semi-synthetic fashion. Amoxicillin, the most common antibiotic which we use, the cephalosporins, carbapenems, and so on. So this is a basic classification of drugs based on their synthetic strategies employed. So how do you analyze these various types of antibiotics? So let's look at the analysis of antibiotics. For antibiotics, the main two methods that we use is LCMS or HPLC. Okay. So for LCMS, liquid chromatography coupled with mass spectrometer detector. So via liquid chromatography, you can separate the active pharmaceutical ingredient, and then you can detect that ingredient using a mass spectrometer detector. Using an electrospray ionization in the mass spectrometer. Of course, if you have studied it, you know that you have to first ionize your analyte and then you have to detect it. So for here we can use the electrospray ionization. We are detecting the positive ion. So mass spectrometer is a plot of intensity versus the charge, the mass over charge ratio. So some of the examples are aminoglycosides, sulfonamides, fluoroquinolones, which are used. Also, we can use LC coupled to a UV or a mass spectrometer as detectors. Cephalosporins are analyzed using this technique. There's also HPLC with UV detection. And in the case where you don't have a component which doesn't absorb in the UV region, what do? You can either use suppressed conductivity detection or a corona charged aerosol detector can be used, or evaporative light scattering detectors, or a mass spectrometer could be used. Electrochemical detectors like amperometers can be used for detection. So these are the several methods that we use for analyzing antibiotics. So with that, I come to the end of my talk. Thank you so much for listening. So We looked at different types of drugs and pharmaceuticals. We went through all the analytics. We went through the official methods, the classical methods, modern methods, and we also looked at we took specifically certain drugs and studied some of the analytical methods which are used for those specific drugs. So thank you all once again for listening.
Thank you, ma'am. Thank you, ma'am. It was a valuable session from you. We had a good sort of attendees from you. We had some questions from some of our attendees. Can I raise the question?
Yeah, sure. Please.
So one of the questions was, can you just brief about pharmacopoeia?
Pharmacopoeia? Okay, pharmacopoeia. Yeah, pharmacopoeia. I had talked about this in the drug. See, pharmacopoeia is nothing. It's a book. It's an official document. അതൊരു ഒഫീഷ്യൽ ഡോക്യുമെന്റ് ആണ്. എല്ലാ രാജ്യത്തിനും ഓരോ ഇപ്പൊ ഇന്ത്യക്ക് ഇന്ത്യയുടെ pharmacopoeia ഉണ്ട്. There is China has Chinese pharmacopoeia, Japan has Japanese pharmacopoeia, there is a British pharmacopoeia. അങ്ങനെ നമുക്ക് ഓരോ കൺട്രി അല്ലെങ്കിൽ റീജിയണൽ pharmacopoeias ഉണ്ട്. യൂറോപ്യൻ pharmacopoeia ഉണ്ട്, അല്ലെങ്കിൽ ഇന്റർനാഷണൽ pharmacopoeia by the World Health Organization, WHO ന്റെ ഒരു pharmacopoeia ഉണ്ട്, which is called the International Pharmacopoeia. അപ്പൊ നമ്മൾ ഇവിടെ ഉണ്ടാക്കുന്ന എല്ലാ ഡ്രഗ്സും അല്ലെങ്കിൽ എല്ലാ ഫാർമസ്യൂട്ടിക്കൽ ഡ്രഗ്സ് മാർക്കറ്റ് ചെയ്യണമെങ്കിൽ അത് നമ്മൾ വി ഹാവ് ടു മെൻഷൻ ഹൗ വി ഹാവ് ഡൺ ദ അനാലിസിസ് ഓഫ് ദാറ്റ് ഡ്രഗ്. ആ ഡ്രഗ് മാർക്കറ്റിൽ എത്തണമെങ്കിൽ അത് നമ്മുടെ ആ രാജ്യത്തിന്റെ റെഗുലേഷൻസ് അനുസരിച്ചിട്ട് വേണം. അതായത് ആ കൺട്രിയുടെ ഫാർമക്കോപ്പിയയിൽ മെൻഷൻ ചെയ്ത അനാലിറ്റിക്കൽ ടെക്നീക്സ് ഉപയോഗിച്ചിട്ട് അതിന്റെ അനാലിസിസ് നടത്തിയിട്ടുണ്ടാവണം. ഈ ഫാർമക്കോപ്പിയ എന്ന് പറഞ്ഞ ആ ബുക്ക് we have it's a book which lists of all the different methods, analytical methods that can be used for each drug, for the different standard analytical methods, even temperature, the apparatus that you use is mentioned. Thermometers വരെ ഏത് ടൈപ്പ് യൂസ് ചെയ്യണം മെൻഷൻ ചെയ്തിട്ടുണ്ട്. the metric, the weights, the measures എല്ലാം ഡീറ്റെയിൽഡ് ആയിട്ട് എഴുതിയിരിക്കുന്ന ഒരു ബുക്കാണ് ഈ ഫാർമക്കോപ്പിയ. അപ്പൊ അതിലുള്ള അനാലിറ്റിക്കൽ മെത്തേഡ്സ് ഉപയോഗിച്ചിട്ട് വേണം നമ്മൾ ഒരു ഡ്രഗ് അനലൈസ് ചെയ്യാനും. അങ്ങനത്തെ ഉള്ള ഡ്രഗ്സേ മാർക്കറ്റിൽ എത്താൻ പാടുള്ളൂ. ഇപ്പൊ നിങ്ങളുടെ വീട്ടിലുള്ള ഏതെങ്കിലും ഒരു ഡ്രഗോ ടാബ്ലറ്റ് എടുത്ത് നോക്കിയാൽ നിങ്ങൾക്ക് അതിൽ കാണാം ഇന്ത്യയിൽ മാനുഫാക്ചർ ചെയ്തിട്ട ഡ്രഗ്, ഇന്ത്യയിൽ കൺസ്യൂം ചെയ്യുന്ന ഡ്രഗിൽ ആ ഡ്രഗിന്റെ ലേബലിൽ നോക്കിയാൽ അതിന്റെ ഓരോ ഇൻഗ്രീഡിയന്റിന്റെ അറ്റത്ത് IP, ബോൾഡിൽ തന്നെ IP എന്ന ആക്രോണിം ഇട്ടിട്ടുണ്ടാവണം. ഇപ്പൊ അത് ഇട്ടിട്ടില്ലേ അതിന്റെ അർത്ഥം അത് ഇന്ത്യൻ ഫാർമക്കോപ്പി അനുസരിച്ചിട്ടല്ല ഡ്രഗ് അത് അനലൈസ് ചെയ്തേക്കണേ, അല്ലെങ്കിൽ അല്ല അതനുസരിച്ചിട്ടല്ല അത് പ്രൊഡ്യൂസ് ചെയ്തേക്കണേ. അപ്പം അതുകൊണ്ട് ആ ഡ്രഗ് ശരിക്കും മാർക്കറ്റിൽ എത്താൻ പാടില്ല. അങ്ങനെ ഒരു ഡ്രഗ് എത്തിയാൽ അത് ശരിക്കും it should not be marketed. It's a criminal offense actually ഇങ്ങനത്തെ ഒരു ഡ്രഗ് മാർക്കറ്റിൽ എത്തുന്നത്. അപ്പം ഇത് വളരെ ഇമ്പോർട്ടന്റ് ആയിട്ടുള്ള ഡോക്യുമെന്റ്. ഇത് റിസ്ട്രിക്ട് ചെയ്യാനല്ല, മാനുഫാക്ചേഴ്സിനെ റിസ്ട്രിക്ട് ചെയ്യാനല്ല. ആക്ച്വലി ഇറ്റ് ഇസ് ഫോർ ഹെൽപ്പിംഗ് ദം, ടു സപ്പോർട്ട് ദം and to make things clear that if you have to market a drug, you have to market it or you have to produce the drug using these standards. അല്ലെങ്കിൽ ഇത് മാർക്കറ്റിൽ ഇറങ്ങത്തില്ല. So it's a very important document for manufacturing and for marketing of drugs.
Ma'am, another question was raised by a student is like that. Please explain the chirality of methyl dopa and thalidomide. Please explain the chirality of methyl dopa and thalidomide.
Chirality of methyl dopa.
It's chirality.
Chirality of L-dopa, dopamine. I think I haven't talked about that in this talk. It might be from one of my previous talks she's talking about. The chirality, they are actually enantiomers, and usually the dopa it is it's a diphenyl compound. If I remember it correctly, it's a diphenyl compound, and it is used and together with the dye, it gives an absorbance which can be detected using a UV vis, and the relative configuration of dopa is L. It is L. Relative configuration. L-glyceraldehyde വെച്ചിട്ട് L-dopa ആയിരിക്കും ഞാൻ ആ ടോക്കിൽ എഴുതിയിട്ടുണ്ടാവാം. L-dopa എന്ന് പറഞ്ഞാൽ നമ്മൾ അത് റിലേറ്റീവ് കോൺഫിഗറേഷൻ ആണ്. അത് നമ്മൾ ഗ്ലിസറാൽഡിഹൈഡിന്റെ കോൺഫിഗറേഷനോട് കമ്പയർ ചെയ്തിട്ട് ആണ് നമ്മൾ ഒരു കോമ്പൗണ്ടിന്റെ കോൺഫിഗറേഷൻ പറയുകയാണെങ്കിൽ അതിനെ റിലേറ്റീവ് കോൺഫിഗറേഷൻ എന്നാ പറയാം. അപ്പം എൽ ഗ്ലിസറാൽഡിഹൈഡ്, ഇഫ് യു ഹാവ് ദ OH on your left side, it is called L. If it's on the right side, it's called L. It's called D. So L-DOPA has the OH on its the particular group. I think it's an amino group which is on the right side. So that is how L-DOPA. It doesn't. It is not from this talk. I understand. It must be from one of my previous talks.
Maybe like that. Another question was raised by a student. Please brief on proton pump inhibitors activities in antacids. Please brief on proton pump
pumping
inhibitors activity in antacids.
Antacid. അപ്പോൾ antacids അസിഡിറ്റിക്കുള്ള ഗുളികകളാണ്. അതും ഞാൻ കവർ ചെയ്തിട്ടില്ല. Actually, right now I'm not in a position to talk about that. Antacids ne kuriche I haven't reviewed it. Yeah.
You have mentioned in stoichiometric methods that terms like coulometry and potentiometry. Can you just brief about that?
Coulometry എന്ന് പറഞ്ഞാൽ നമ്മൾ titration തന്നെയാണ്. Basically, it's a titration method, titrometric method. What you are measuring, it's not the color. You're not looking visually measuring the color, seeing the color change. The end point is not by a color change. End point measuring is നമ്മൾ ഈ current ആണ് measure ചെയ്യുന്നത്. എന്നിട്ട് ആ current measure ചെയ്തിട്ട് ആ current എത്ര current ആണ് produce ചെയ്യുന്നത് അതനുസരിച്ച് നമ്മൾ അതിനെ concentration-നോടാണ് relate ചെയ്യുന്നത്. So it is an analytical quantitative method in which you are getting a concentration of an analyte by measuring the current. Whereas in a potentiometry, you get the concentration of an analyte by measuring the potential difference. Working electrode and reference electrode and down. You change the potential. You get a change in there will be a change in potential, and as the reaction proceeds or as the titration proceeds, and you're basically measuring this potential difference in potentiometry. So that's how you do potentiometric titration for analyzing or getting the concentration of an analyte.
Okay, ma'am. Time is running up, so we have almost reached all the questions. Some of the questions are still there. I will mail you the rest of the.
Okay, sure.
So it's almost done. So thank you almost on the behalf of myself and on behalf of ASAP also. Thank you so much, ma'am. We will wind up the session for tomorrow. Thank you, ma'am.
Thank you.